Hello and welcome back to Calculus 1, section 3.8 on implicit differentiation. So this is another rule that we use. This time we are going to take derivative of curves that are not functions. So before we dive into that, I'm just going to put a couple of these, I'd say, interesting things here. So when you write y equals f of x, that will be explicit form. And you are able to separate x's from y's and have y equal everything else. So, and that's your standard function, right? So, examples like y equals x squared, y equal 3 sine x, y equals e to the x over 4 plus square root of x, whatever, right? But you see the idea. You are able to write y equals, and then everything that goes on the right is in terms of x's. And then we have something that looks like this. F of x y equals 0, which is implicit form. Now, could be functions, but it doesn't have to be functions. And for this particular one, what you have is, example, x squared plus y squared is equal to, let's say, 9. This is a circle, and the circle is not a function. You also have x equals y squared, right? That's a sideways parabola. Also cannot isolate. Maybe y equal, no. I mean, I could have, but y sine y equals x plus 1, whatever. You can't write any of these formulas as y equals everything else. So you have this as one set and this as the second set. So far in chapter 3, we dealt with number 1. And you had all of your basic rules. You had your product rule, your quotient rule, right? You had your chain rule. So all of those rules were there. But see, when you get to the second part, which is what we are going to talk about today, which is implicit form and implicit differentiation, right? You realize immediately that, right, these are curves as well. They're not functions, but they can be graphed. And when you graph them, they get tangent lines, right? So if there is tangent line, there is the derivative that gave that tangent line. So if we, jump here and put x squared plus y squared equals 9, you get a circle with the radius 3. So, okay, that's great. If you go and say x equals y squared, as I said, you get that sideways parabola. And the sideways parabola is not a function because it fails vertical line test. Now, all of those have tangent lines, right? I can go to a certain point, let's say 1, 1, and draw the tangent line. Now, that tangent line, the slope is computed through the derivative, which means that we can find the derivative of these things, right, of these implicit forms. We just need to figure out the way to do it. The last example I had was y sine of y equals x plus 1. All right. Clearly not a function, right? Clearly not a function, but it's definitely something that we can find derivatives at every point because the whole function is smooth and curvy, right? So we can find tangent lines. So now that we understand that these functions, the curves, right, have tangent lines, we understand that. Now let's figure out the way to find those. And it is actually the procedure. There are no formulas for this one. It is a rule which uses a chain rule, which says that every time when you are taking the derivative in respect to a variable, right, off of the same variable, you will write the chain rule. So let's say you take the derivative of x in respect to x, you will write dx over dx. If you take the derivative of y in respect to x, you will write dy dx. Later on, when we start dealing with volume and area and all that stuff, if you take the derivative of volume in respect to time, you will get dv dt, because you are taking the derivative of v in respect to t, so dv dt. So now we are just going to take this, everything we learned, one step higher to include the chain rule, and then we're just going to start ignoring when the dimensions match, when the variables match. So here is an example of x squared plus y squared equals to 9 as we take the derivative in respect to x. So we take the derivative term by term. So what is the derivative of x squared? 2x. And then we will follow with the chain. We took the derivative of x in respect to x. Okay. Plus, what is the derivative of y squared? 2y. And then you follow with the chain. We took the derivative of y in respect to x. Equal. What is the derivative of 9? 0. Derivative of a constant is 0. Now dx over dx will cancel. No need to have that. And now you solve for dy dx. So 2y dy dx is equal to negative 2x. dy dx is equal to negative 2x over 2y. And that is equal to negative x over y. And there's your derivative. dy dx is equal to negative x over y. That's the derivative of the circle. And we see that the derivative of the circle actually doesn't depend on the radius, so it doesn't depend on the size of the circle, which is really awesome. So this is the full problem. And we are doing now something that we haven't done before, and that is every time when we take a derivative of a certain variable, we immediately follow with a chain. I took the derivative of x in respect to x, so dx over dx. I took the derivative of y in respect to x, so dy dx. And no matter which letters you use, it is always going to be, I took the derivative of blah in respect to blah. So you have the two values. Now they can be the same. If they're the same, they cancel. We don't need to write them. So technically, this one was there all along from lecture 1. We never wrote it down because we didn't have to. dx over dx, because all of our derivatives were always in respect to the main variable we were concerned with, right? But now you can have as many variables as you want, and you will be taking the derivative in respect to a single variable. This is extremely useful when you are learning physics and using physics to design and develop things in engineering and so on. One of my favorite examples is obviously ideal gas law, because for whatever reason, most of the students remember that particular formula. But if you consider that formula, so PV equals to nRT, and then this nR is actually a constant, so I'm just going to call that constant K so that we don't have to worry about it. So I'm just going to go PV equals KT. P is the pressure, V is the volume, and T is the temperature. Now this is ideal gas, but you know, it's close enough to the gases around us. What we see is that the pressure and the volume and the temperature are all related to each other, and the greatest thing is that I can take derivatives in respect to any of the variables to measure their change in respect to any of the other ones. So I can take, let's say, the derivative in respect to pressure. So I have a product rule on this side and just a single function on the left-hand side, because again, pressure is changing, volume is changing, the temperature is changing. So if I'm taking the derivative of PV equals KT, all I need to do is to make sure that when I'm taking the derivative of the same variable, right, I can put dP over dP. When I'm taking the derivative of a different kind of variable, I have to follow with the chain. So now, obviously, what this is actually is the problem 311. But we're only doing the calculation part of it, not the concept and setting up and all that kind of stuff. So it's okay. So what I have here is product rule. So copy the first and then derivative of the second. And since I'm taking the derivative in respect to P, the derivative of V is 1, right? It's like derivative of X is 1. Derivative of V is 1. And then followed by dV dP because I'm taking derivative of volume in respect to pressure. Plus, copy the second one, which is V, and then times the derivative of the first. Derivative of P is 1, and then dP dP because I took the derivative of pressure in respect to pressure. That will cancel. On the other side, we just have copy the constant. Derivative of the temperature is going to be 1 again, and then you took the derivative of the temperature in respect to pressure. When you simplify this, oops, supposed to be, come on, there's lag. Thank you. So plus V is equal to K dt dP. This is what implicit differentiation does for you. It gives you the formulas where you can measure the change of different quantities, physics, engineering, right? Which is why, obviously, this course is extremely important if you are actually going to be an engineer or something like that. So, starting from the basic concept and then deciding that you need to measure things in terms of change of the pressure. But maybe you're not going to do the change of pressure. Maybe you want to do the change of temperature. Maybe you want to do the change of volume. Change of temperature is generally what you should be concerned with. You will find way more shredded tires, right, on the highway in the summer than in the winter. Why? The heat, exactly. As soon as you increase the temperature, because the outside is 105 degrees, plus the heat of the tire, which is the friction between the tire and the road, and then people don't adjust the pressure, right? You have to lower your pressure in a tire over the summer. That's common sense, otherwise you might die. It's very simple, it's a survival technique. Your pressure in tires have to be lower in the summer and higher in the winter. So there is a formula that shows why. If your volume of the tire is the same, it's not a balloon that you can inflate until it pops. For the constant volume, what happens? If volume is constant, if the temperature goes up, what goes up? Pressure. Pressure goes up. Now what happens when the pressure goes up? Exactly. So, it was well timed. So when the pressure goes up, yes?
So for the second part, like on the right side and the equal sign, how come you did, like, are you supposed to do the product rule for the second, for the...
K is constant. So think of it like 9t. You don't take the derivative of, you don't do product rule for 9x, right? You copy 9. So when you have so we're not doing the details of this because, again, this is going to be flashed out in 311 next week. So constant you always copy for the derivative, and K is a constant in this case, so you just get to copy it for the derivative. So the knowing which one's the variable and which ones are the constants is important. So that's the talk about the basic of implicit differentiation, and now we just do a whole bunch of problems. You've seen the implicit differentiation basic idea. You have seen also the application, but you will see obviously much more of this stuff in 3.11. Let's take a look at all the other problems that I mentioned. Now, what I want to do here is I want to go and see the derivative in respect to x of x equals y squared. That was that sideways parabola. So what would that derivative be? What's the derivative of x, guys? 1. You took the derivative of x in respect to x, that will cancel. What's the derivative of y squared? 2y. Took the derivative of y in respect to x. Great. Dx cancels. So dy dx is equal to 1 over 2y. Now over here in orange, d dy of x equals y squared. Just because we can. Work that one out on your own. You're going to get the same or not the same?
No, it's not the same.
Not the same, good. What is that one? Oh. What's the derivative of x? 1. And then we follow with what? Dx dy. Good. We took the derivative of x in respect to y. What's the derivative of y squared? And then dy dy, which we don't have to write, but we still do. That will cancel. And we have dx dy is equal to 2y. Come on, say it. They are not reciprocals. They are the same. Flip the one on the right, because for fraction, if you flip one side, you have to flip the other one, right? Flip it. What do you get? They are the same. Cool.
You lost me there. So why would you flip it?
It's a fraction. You can flip it. We got dy dx, dy dx. So if you take the derivative in respect to y, solve it, and then flip it, you get the same opposite. It's cool. You can do it. All right. Let's see the other problem that I had over there. Actually, let's try something else. Let's try some of the simpler examples. 3x squared plus 6y equals to 4xy. Okay, let's take a look. The derivative of 3x squared is 6x dx, right? Cancels, so we don't care. Derivative of 6y is 6 dy dx. Very good. Excellent. And what do we have on the other side? Product rule. There was the trap. It's the product rule because you have a function 4x, which is a linear function, times a function y, right? So I'll write it here in blood. 4xy is a product rule with the stick at the back. All right, so now copy the first 4x. Derivative of the second is 1 dy dx. Plus, copy the second one, y. Derivative of the first is 4 dx dx. Now we massage this with algebra to get dy dx alone, and we are done. So, product rule, we have our u, we have our v, so we have our u, we have our v prime, plus we have our v, and we have our u prime. So product rule is 100% there. All right, so now move all of the terms with dy dx to the left side. So 6 dy dx minus 4x dy dx. And then move all of the terms without dy dx to the right, which is 4y minus 6x. Factor out dy dx. You are left with 6 minus 4x equals 4y minus 6x. Divide by it. So dy dx is equal to 4y minus 6x over 6 minus 4x. Divide by 2 because we can. Dy dx is equal to 2y minus 3x over 3 minus 2x. Cool, huh? Let's take a look at that problem that I gave up there. Y sine y equals x plus 1. Derivative in respect to x. What do we have on the left?
1 times cosine y plus sine y
You're missing.
times 1.
You are missing dy dx
dy dx.
because So when you have a product rule. So when you copy the first, take derivative of the second is cosine y, and you have to put dy dx because you took the derivative of y in respect to x. Plus copy the second one, which is sine y, and then derivative of the first is 1. You still have dy dx because you took the derivative of y in respect to x. On the right hand side, the derivative is 1, and then dx, but that will cancel. So now, when you factor out dy dx, you get y cosine y plus sine y equals to 1, and the derivative is dy dx equal to 1 over y cosine y plus sine y. Ta-da! One more application. Problem. So we had, right? So this one is going to have x squared plus y squared minus 1, everything cubed, minus x squared y cubed equal to 0. And let's find the derivative of x. This one is not easy. right. This one has what?
Mess.
Chain rule because of everything to the third, and then it has a product rule in the second term, right? All right. Let's go. The derivative is 3x squared plus y squared minus 1 squared times the derivative of the inside, which is 2x plus 2y dy dx, right? So that will be the derivative of the first. You have the chain rule, so 3 drops down and 3 minus 1 is 2. And then derivative of the inside, 2x 2y dy dx, derivative of negative 1 is 0. Minus, and now we have the product rule here. Copy the first. Derivative of the second, don't forget dy dx because you took the derivative of y in respect to x. Plus copy the second, which is y cubed, times 2x, and then everything is still equal to 0. This? Yes. Because you copy the second and then the derivative of the first. Good. So now, we distribute this here and here because we have to separate these terms because one has dy dx, the other one does not. And then we distribute this minus sign to both. And then we should be okay with the rest. So distribute, we get 6x x squared plus y squared minus 1 squared, no copying, plus 6y x squared plus y squared minus 1 squared dy dx. Minus 3x squared y squared dy dx minus 2xy cubed equal to 0. Now, terms with dy dx stay on the left. The other terms get kicked outside. So factor out dy dx. And you are left with 6y x squared plus y squared minus 1 squared minus 3x squared y squared. There we go. Equal to, kick the other terms to the other side. So that's 2xy cubed minus 6x x squared plus y squared minus 1 squared. And now just divide by this expression. So dy dx alone is 2xy cubed minus 6x x squared plus y squared minus 1, everything squared, divided by 6y x squared plus y squared minus 1, everything squared, minus 3x squared y squared. When you have this derivative, you can find the tangent line and to any point x and a y that it's on the original curve. Yes?
How did you factor out a dy over dx if the 6x and that big giant thing in the first term and the last term you don't have dy dx?
Oh, these are moved to the other side. See, this term is right there. So there's a minus, it becomes a plus here. And then the first term is moved here as a negative. So all of the terms without dy dx are moved to the other side, right? So this is what applied problems look like, right? Here is the application. So you can see I typed in the function. I mean, it's not a function, sorry, it's a curve. Ready? Equal to what? So now you know what the derivative is. What happened?
It's like a nice Valentine's Day thing.
Yeah. Just write this on a piece of paper like that. You know, just give it. They have no clue what it is. Just ditch them right away. They're not for you.
That's how math professors.
Cool. So now you have that application. Can we make this worse? Clearly, right? How about a second implicit derivative and a third implicit derivative and the fourth? Not this function because we will be done by Thursday of 2021. But how about something simple? So let's find the second derivative for circle because we can. Oh, I can't separate because of internet. So higher order derivatives. Find the second derivative for x squared plus y squared equals to, let's say, 16. So circle radius 4.